At this point, ANSYS has the equations that we wanted to solve. To see that, let me go to the workbench window. We started off by dragging static structural into the project page. So that was one clue. And then under geometry, we have given it a single part that has a volume. So we wanted to solve a static structural problem over a volume, and it's using those two clues. So it's using static structural and the volume and saying, oh, you want to solve the equilibrium equations over a volume. You can also do static structural problems over lines and areas, which uses a different mathematical model. Let's not get into that. So using those two clues, it says, oh, you want to solve the equilibrium equations in the x direction, something like this, which we saw in pre-analysis. And then the body force term, which is 0 in our case, and that's a default in ANSYS. So that's the x direction equilibrium, and similarly y direction equilibrium, and I won't write it out in the interest of time, and the z direction equilibrium. Again, I won't write that out. In fact, if I go back to the pre-analysis, okay, so it's turned on those equations. The body forces are 0 by default, and then these have to be written in terms of the displacement. So you have to bring in the Hooke's law, and so ANSYS has turned that on too, and it's using the default values as of E and nu, which are for structural steel. And to see that, if I go back here and highlight our part, you see that the material assignment is structural steel. That's a default. So we need to change that to the values of E and nu for our material. We'll do that. And then the final set of equations is the strain displacement. And again, that's the equation that's turned on, and there are no constants appearing in that. So the only thing we need to do now is to specify the right values of E and nu. So let's do that. I'll go to the in fact, if I go to the problem specification, I see the Young's modulus is 1 e to the power of 7 or 10 to the power of 7 psi, and the Poisson's ratio is 0.33. Let's specify that. So I'll go into the project page, double click on engineering data, and I'll add a new material. So I'll call this aluminum 6061 T6. You can give it any name you want. I'll hit enter. And then you will probably see something like this. So expand linear elastic. And you can double click on isotropic elasticity, or I like to drag it over to the material. And then it says, oh, okay, so you need those two constants in your Hooke's law. And I will change the units to psi, which are not my favorite units, but we'll stick with it. Oops. So I need it as 1 e to the power of 7 psi, and 0.33 is the Poisson's ratio. Okay, that looks right. And so I'll hit enter, and so you see I have the material with the right Young's modulus and Poisson ratio. And then I go to the project page, and so I made a change in engineering data, and to bring it into model, which is downstream, I have to right click and say refresh. And now if I go back to mechanical, and under material assignment, I'll see that new material, and I'll select that. Okay, so this means that it has E is equal to 1 e to the power of 7 psi, and nu is 0.33, which is what we want. So at this point, ANSYS has the governing equations that we want to solve, the equilibrium equations coupled to the auxiliary equations, and it knows the domain over which we want to solve those equations. The last step in defining the mathematical model is specifying the boundary conditions at the edges of our domain, and that's what is coming up next.